So this section of video will talk about what does it mean to be increasing or decreasing? What does it mean for a function to be doing those things? And I think you have a pretty good understanding of what it means already. Increasing means as you go from left to right, you go uphill. Decreasing means you're going downhill. Now they do have kind of a fancy definition throughout here, so I just want to briefly explain that. It says that if we are looking at two x values and we have one that's smaller than the other, so that's what I have right here. If something is going to be increasing, then we're going to be looking at what's going on with the y values at those points. And so basically it's saying that if it's increasing, the y value at this point would have to be smaller than the y value at that point. And then as you connect them, you see that, yep, it's going uphill. That's the general idea of what it means to be increasing, or you flip it slightly for it to be decreasing. So we're going to look at this graph right here and basically say where is it increasing, decreasing, or constant, and then also compare what the derivative is doing at those places. So when we're describing these things, you're going to give me a range of x values where the function is decreasing, increasing, or constant. And so for the first part here, it's going downhill. So from the x values of 1 to 3, it's decreasing. From 5 to 7, it's increasing. And from 3 to 5, right in the middle there, those x values, it's constant. And just kind of a notation thing, when we define this, we do use parentheses for this. We say that at point 3, it's really not decreasing, it's really not constant, that's where it's changing. So technically we use parentheses, so we don't include the x value of 3 there. Now I want you to think about what's going on with the derivative at these intervals. If we just look at the decreasing section, for example, remember that the derivative is the slope of the tangent line. And so any tangent line that I would draw in here, its slope would be negative. And wherever it's increasing, those slopes would be positive, and where it's constant, the slopes are 0. So really our goal in this section of video here is to just simply make this connection, and then to use that to solve some sort of application questions. So on this slide they actually have written down that rule. Basically, if we know that we have a function that is continuous on a closed interval, so the endpoints are included, and it's differentiable on the open interval, so you don't worry about the endpoints so much, but it's going to be a nice smooth function. If that's the case, then we can use that general idea of if the derivative is positive, then the function is increasing. If the derivative is negative, it's decreasing. Derivative is 0, it's constant. Now, I want you to think about how that's going to help us, or how we would use that to figure out where the actual function is increasing or decreasing. So let's just say that we had this function here that I just drew in, just an upside down parabola. If we wanted to know where it's increasing, we can look at the picture and we can pretty much say that's where it's increasing and here's where it's going to be decreasing. But if we didn't have the graph, how would I figure that out? Well, I know that this max right here is going to be kind of important. That's the cutoff for where it makes that switch. And so algebraically speaking, we know that that high point is going to be wherever the derivative equals 0. So as we go through some steps for figuring out where it's increasing or decreasing, and later on in a future video where we have maxes or mins, we first of all find critical points. Okay, critical points where the derivative is 0 or undefined. From there we do a little testing on either side of those points. We can use a sign chart to kind of help out with that, and then we need to be careful with how we write or justify our response. So we have at least one example here that we're going to go through, 2 examples I believe, of how we actually set this process up. So the first function here is x cubed minus 12x minus 5. We just want to know where it's increasing or decreasing. You can graph this on your own if you want to. Our goal here is to figure out how to do this without graphing. And so our steps say, think about where there might be maxes or mins, and that means where is the derivative going to equal 0, or where is it undefined? The derivative of this function would be 3x squared minus 12. Now that's just a normal polynomial. That thing will never be undefined, so really we're going to be worried about where this is going to equal 0. So how do we go ahead and set that up? I'm going to bring that negative 12 to the other side. I'm going to add 12 to both sides basically. Divide both sides by 3. And so I would get x potentially equaling positive or negative 2 as my critical points. So this is kind of step 1 on the above chart. Okay, steps 2 and 3 involve making a sign chart for the first derivative. So first thing, a sign chart, something like that. We're just going to define it as f prime. And we said that -2 and +2 are important parts. So what I'm going to do is I'm going to pick values in these 3 sections and test it in that first derivative. And from that, I'm going to be able to figure out if something is increasing or decreasing. So if I were to, let's just say, plug a 0 in there. If I plug a 0 in here, my first derivative equals -12, and I'm really just worried about the sign. It's going to be negative in between. If I were to pick maybe a +3 there, okay, I put a 3 in right there. I square that. I get 9. 9 times 3 is 27. 27 minus 12 is +15. But again, I'm just worried about the fact that it is positive. And then maybe I'll pick a -3 for that last section. I plug that in there. I go through and do that, and I'm going to get a positive answer as well. So what does this tell me? Let's see. This is kind of steps 2 and 3 right here. Basically, if I were to sketch this, just do a very brief sketch, it's telling me that at -2 and at +2, I was increasing, and then at -2 it changes sign, so now I'm going to be decreasing. And right here it changes again, so now I'm increasing. Now I don't know if the heights of those y values are correct, but I know that's going to be the general idea. And if I go back to the original function right here, that would make sense with a cubed function, especially with the way that that leading coefficient is positive. This would match up with x cubed. So it's going to do something like that. I'm not really worried about this picture at all. You don't have to show me that at all. You can just do this work, and then from there we're going to write out a nice little response right there. So this is basically how you would write out your answer with a justification. You'd say that the function f of x, so you actually have to name the function, it's increasing on these intervals. So here's our x values. It matches up with what we see on our sign chart up there. And the justification or the reason, because we have this test, is since f prime of x is greater than 0 on that same interval. Okay, so just a couple things to note. First of all, never use it. Okay, never use pronouns, because the graders of your test they're not sure what you're referring to. So I always make sure that I'm labeling the function and labeling the derivatives exactly what I'm intending to say. The second thing is I'm only answering part of the question here. I would write something very similar for the decreasing part. I change that. I change the interval so it matches up. I change this so it says it's less than 0. But other than that, the writing is going to be the same. So to fully answer the question, you really have to write this all out again, but do it for the decreasing parts. Okay, jot down any questions, and we'll move on to our last example. So for this one, we're looking at the function x squared minus 9, all of that raised to the 2/3 power. Basically, the work for this is going to look exactly the same. So I'm probably going to pause and just write out a bunch of stuff, talk you through it, pause again, write out some stuff, just for the sake of time. So the first thing I'm going to do is actually take the derivative, and so you need to recognize we're going to have to use the chain rule for this. So the power of 2/3, I bring that down to the front. The new power is 1 less, so 2/3 minus 1 is -1/3. This stays the same, and then the derivative of that inside part gets tacked on at the end. And then if I just kind of rearrange some things and I write it in a simpler way, the 2 times 2x is a 4x. The 3 goes in the denominator. When we have a negative power, we can put it into the denominator and make the power positive, and so really that's kind of saying the cube root of this whole chunk. But that's going to be a little bit easier way of thinking through it. So from there, we need to know, where does f prime equal 0? And so f prime would equal 0 when the numerator is 0, and so that's going to occur whenever x equals 0. So that's going to be one of our critical points to think about. And f prime is undefined whenever the denominator would equal 0. And so that's going to occur, if you think about that, how do I get that stuff in the parentheses to equal 0? That's going to occur at x equals positive or -3. Okay, so we have our 3 critical points, and now I'm going to make a sign chart to check that. By the way, that was step 1, and then over here we'll do steps 2 and 3 together. So I make a sign chart. I've labeled it as f prime, and then here are my critical points, and I'm just picking values in between those numbers and figuring out the overall sign of that derivative for those intervals. So maybe I picked a positive 1. If I put a 1 in here, the numerator will be positive, and then down here I'd have a negative 8, the cube root of negative 8. That's going to give me a negative answer times 3. It's still negative, so I have positive divided by negative. That means that my derivative for that interval is negative. So I went through and I kind of did that 4 times just to make sure. And so now I know that from negative infinity to negative 3 it's negative. The derivative is negative. That means that the slope is decreasing, or the function is decreasing. The slope is negative for the original function. Same thing here. And for these two, the derivative is positive, meaning I have positive slopes, meaning the function is increasing. So now I just need to write that out in a nice sentence again, just like I did with step 4 before. So again, I'm just focusing on the increasing part. You do basically the same thing for decreasing, you just change a few things, but we say the function f of x, we name the function, it's increasing on this interval, so a set of x values or a range of x values, and because we know that the first derivative is positive there, and that's enough as far as a justification for proving that the function is increasing or decreasing. Jot down any questions and we'll see you in class.